great pleasure to be here and tell you about our research. And we're relatively a new group at San Diego State. We're 10 months old, and I'm going to tell you about C1 biocatalysis. And C1 because I'm going to talk about single carbon compound. And my favorite one is methane. And I believe many of you heard about methane already because it is high energy clean fuel and it's feedstock for industrial synthesis. But at the same time, it is a very powerful greenhouse gas which accelerating the rate of global warming. We also know that today methane is readily available and cheap carbon feedstock. But because it's readily available and very cheap, methane emissions grew significantly in past 7 years. Fossil and renewable, this is what trademark of methane is. Fossil today, biogas renewable tomorrow. But I want to mention to you that this renewable very often today is unwanted, fugitive byproduct that people try to get rid of. And one way how we get rid of this methane is flares. This is what a reporter told after visiting North Dakota. It looks like a birthday cake out there at night. Why? Because this is where shale gas production is. This is where unwanted methane comes out. And to get rid of this unwanted methane, it just flared. I want to mention not natural gas is flared, biogas that is produced at wastewater treatment facilities. Biogas is also flared. Why? Because it's remote location, nobody needed such remote. Typically low pressure, purity is too little methane, too much CO2, and contaminations that really hard to get rid of. So I want to mention to all of us emit methane as well. This is a slightly different picture of Boston, and what this picture demonstrates for you, this is pipelines, natural gas pipelines that emit methane daily. A little bit parts per million here, parts per million here, parts per million here. But we emit tons of methane. What to do with that? Okay, one solution is tighten nuts and bolts, and it's really great. But for some ecosystem, it does not work very well. For some pipes, you can't really tighten nuts and bolts. And I want to take you to the most natural way how nature deals with methane, because methane is a part of carbon cycle as well. And the most natural way of dealing with this is microbes, microbes that can eat methane. What we are trying to do here, we are trying to develop a new technologies as a new microbes-based platform to deal with fugitive methane. And I want all of you to meet my microbe, because for me it's the best microbe. And this picture was done by David Collins with colleagues from Dr. Fry lab as well. So it's very new, it's like 2 weeks old image. It's very beautiful for me. What I want you to remember is that this microbe can burn methane to yield energy and water. This is something we cannot do. We burn methane to get heat. We cannot do it in a small step to get energy out. Another point, it can yield water as well. What this microbes does, it converts methane into simple sugars. So basically methane comes to glucose. And from this point, this microbe is very similar to yeasts, our E. coli. It means that we can use the same metabolic framework to convert methane into different chemicals. Just a little bit more biology, and microbe name, all microbes have name, it's Metallomicrobium alkylophyllum 20Z, gamma proteobacteria, the same as E. coli. It was isolated from very harsh environment, alkaline and soda lake. What that means? It means that it's very robust. It's really hard for undergraduate students to kill it. But it's really good for technology. It also means that it can tolerate high osmolarity and dryness. We have genome. We know that we can manipulate and play with this microbe. Our publication, Genome Scale Metabolic Model, was just accepted in microbial cell factories, and it means that we can play in silico with this microbe. Overall, what we are doing, a short summary. We look on enzymes, pathways, cells, and ecosystems in which this microbe play a key role. We also develop new strategies to improve sustainability of human-made ecosystems. And the final part that we just started here with Lisa Waters, we're trying to find new strategies to adapt to climate change in nature. And we want to talk about carbon in water cycle in dry ecosystems. I have only 10 minutes, very strict, so I will talk only about new technologies, and I will tell you 3 stories. My story 1 is oily, our fatty story, and this is methane to biofuel. Already 3 years old project, and it takes a village to build a new technology, and we have a really nice village here. It's University of Washington, LanzaTech, NREL, Johnson Matthey, and UCSD. If you will look on this microbe, all these are membranes. In biology, membranes are lipids, lipids are biodiesel. So what we are doing, we're going after stranded, our remote natural gas, and we try to convert it into these lipids and then extract those to get biodiesel. This is 1.5 grams of real biodiesel from methane-trophic bacteria. For me, it's the most expensive fuel I ever saw, but it's here. We can do that. We just have to optimize the technology. My story number 2 is methane to adipic acid. And this is a new story that is just started. What is adipic acid? Adipic acid is the most important industrial acid, and it's used for plastics, for paint, polyurethane resin, low temperature lubricates, and synthetic fibers. And I wanted to share this with you. All of you should think that I requested from WDRB this report that came out today, this morning, which would demonstrate that adipic acid market is expected to grow. And this is really great when you start to develop a new technology. Again, we have another village here, NREL, National Renewable Energy Laboratory, Pharmatics, Metabolon, and North Carolina State University. We after biogas to modify this microbe to produce more adipic acid with immobilized cells, and it includes product recovery, and here is our product. And my last story, which I believe my favorite, and it's sweet story because it's methane to sugars. I mentioned to you these microbes can convert methane directly to sugars. What I didn't mention to you is that these microbes can accumulate 16% of their dry weight sugar. 16% is the same as sugar cane. Sugar cane, it means that you can extract that. What we want to do actually, we would like to develop technology in which all fugitive methane will be captured and transformed into sugar, which you can extract and supply for any other different technologies to drive biocatalysis. And of course, any technology is nothing without great team. I'm doing very well. I can spend 2 minutes to talk about my team. And I have a wonderful team of people working with me here in San Diego State. Most of them are undergraduate students. Most of them like to come to my office and say, oh, I have a new idea how we can fight fugitive methane. Great, let's move it forward. And of course, number of collaborators and great funding from Department of Energy. Thank you very much for your attention.
Questions?
Very interesting, thank you. I'm sure you know that one of the main problems in renewable energies is storage. Is it even possible to think about some of these microbes as energy storage, little factories?
Thank you very much, because Lutz here. Because for me, I always like to call this microbe a capacitor. Look on this membrane, stack of membranes. I believe they not only harvest this energy, they store this energy. And we have no idea how they do that. We would like to know that. Yes, I think that it's an incredible system, incredible capacitor, which we should learn about, how they can do it. Yeah.
I was just wondering, what is the energy gain ratio now you have, what you get out divided by what you put in, and where do you think the ideal ratio will be in the future?
All right. So this is something that when we have to talk with chemical engineers, they always will bring that. All right, so I will just take this microbe from nature as it is. It will take methane. It will use 40% of carbon to produce energy, and it will use 60% of this carbon to convert into biomass. So 60% is incredible. I would say it's an incredible system already. We have a few steps in which we would like to improve it to 70 and 72. Can we get better? No. And people ask me about that, can you have 100%? I'm saying no, because our methane is our energy source. If we will supply the system with hydrogen, we can get higher. But hydrogen comes from methane, so you just kind of trick the system. No, it's just 70, I believe if we will get to 75, that's the best.
Marina, you were asked about storage, then you were asked about efficiency. The next question is, what about scale up? How many of these bacteria would it take to solve our problem of the amount of methane in the atmosphere?
And I can answer you again. Do you want to scale up this? The big challenge, if you want to scale up, you go after Fisher Trough. You have 100 kilometer square facility to take natural gas and produce chemicals. This already exists. What you're really dealing here with this, ppm here and ppm there, it's not scale up. How small you can do, how scalable technology is. This is a main challenge. Now, biology will never be as large as Fisher Trough, and I don't think it needs to be that large. Actually, I'm personally think that small cartridge that can purify small farm emission is already great. This is the main target.
Very, very fascinating work that you're involved in. To what degree have you had any discussions with respect to commercializability and path to the market?
Kyle, can you answer and help? Technology transfer people here. All right, so we have 5 patents already. We have the first one with San Diego State. Okay. Now, which way we'll go, will they really bring money? I can't answer you. We're so early in the technology that for me as a researcher, this is an exciting place to be. I wish this technology will go to market. I really hope it will, because we should do something. We ignore methane for such a long time that we should do something. And I propose to do it natural way. Now, we have a bunch of new patents cooking right here next door, and yeah.
Well, that's why we have an I-Corp program here on campus. We need to speak with you.
All right, thank you.
Other questions? All right, let's thank Marina.
Okay, thank you.